All right, we're back, folks, and as promised, I'm going to help you guys out with assignment 31 from your manual. Now that's textbook pages 353 to 354, numbers 20, 21, 28, 31, and then 33 through 35. Now, instead of just giving you all the answers and showing you all the work for each problem in great detail, I'm going to change it around a little bit. Now this might surprise some of you, but on the previous assignments, some students just copied my work instead of pausing, starting, and trying to get an understanding for what I was doing. And as a result, they got great homework scores, but their exam scores for the same material were not very good. So rather than giving you all of the answers and showing you the work for each problem in great detail, what I've decided to do for some of these questions is to do similar problems for you. So they will be similar to the ones in the textbook, but not identical to. So please pay attention. For instance, number 20 reads, calculate the molar enthalpy of vaporization of a substance given that 0.433 moles of the substance absorbs 36.5 kilojoules of energy when it is vaporized. Now that's what the problem reads. That's not the one I'm going to do for you. Okay, so problem 20 says you have 0.433 moles and it takes that much energy to vaporize it. Now of course that's going to be the energy required to vaporize this many moles at its boiling point. So we are asked to find the molar heat of vaporization here. So I am going to find the molar heat of vaporization for a different substance. I am going to do it for water. Let's say that 0.691 moles of water at its boiling point requires 28.2 kilojoules of energy to vaporize it. Now that's enough information for me to find the molar heat of vaporization for water. So the molar heat of vaporization would be kilojoules of energy per mole. Okay, that's going to be the delta H of vaporization, and it'll be kilojoules per mole. Now, in our notes, we did kilojoules per gram, so please note the difference there. So, how many kilojoules are required? Well, 28.2 kilojoules are required. To vaporize how much water? Well, 0.691 moles of water. So I've established my unit, kilojoules divided by moles. Isn't that my unit for heat of vaporization? So, I've previously done the math. 28.2 divided by 0.691 gives me 40.8 kilojoules are required to vaporize each mole of water. Now that is similar to the question that's asked on number 20, but not identical to. Next up is number 21. Now for 21 it says, given that a substance has a molar mass of 259 grams per mole, it actually says 259.0 grams per mole, and a 71.8 gram sample of the substance absorbs 4.307 kilojoules when it melts. Okay, so this is the energy that it absorbs when it's at its melting point and it melts. Part A says calculate the number of moles of your sample. So for this one, I'm just going to tell you, you are going to go from grams, 71.8, into moles. You should all be able to do that. Part B says, now calculate the molar enthalpy of fusion. Doesn't that have the unit of kilojoules per mole? Remember, you'll have found the number of moles from part A, and the number of kilojoules are given. So think about that one. You should be able to now handle number 21. Next up is number 28. So we're going to have to turn the page for that one. And that one reads, Water's molar enthalpy of fusion is 6.009 kilojoules per mole. Calculate the amount of energy that is required to the amount of heat required to melt 7.95 times 10 to the 5th grams of ice. So, I'm going to give you a similar problem. It's not the same one. So in my problem, I have a substance whose molar heat of fusion, so delta H of FUS, molar heat of fusion, is 15.5 kilojoules per mole. And I want to know how much heat is required to melt 393 grams of this substance if its molecular weight is 259.0 grams per mole. So here we go. I'm going to start with 393 grams of my substance, and I'm going to go from grams to moles of my substance. 1 mole of the substance has a molecular weight of 259.0 grams. Then I'm going to go from moles to kilojoules, because my question is how much heat is required. So kilojoules is my unit of heat. Well, let's see. Doesn't it say that 15.5 kilojoules are required per mole? So I can use that as a conversion factor. 15.5 kilojoules per mole. Now let's see if my units work. Grams divide out, moles of my substance divide out. I'm left with kilojoules. And I do the math, round off to 3 sig figs, and I get 23.5 kilojoules are required. Okay, now once again, this is not problem 28, it is one that is similar to problem 28. Now, next up is number 31. And I have decided that you are going to be on your own for number 31 except for this little bit of help. You will go from grams to moles, and then you will go from moles to kilojoules. Now, doesn't that look familiar? Hint, see the one above, 28. Okay, then we have to do numbers 33 through 35. So let's take a look at number 33. 33 reads, the following liquid vapor system is at equilibrium at a given temperature in a closed system. So it says we have a liquid plus energy is at equilibrium with its vapor. Now we can write this as liquid is at equilibrium with its gas. Vapor and gas are synonymous. I'm going to put the symbol delta H on the left-hand side. Think back of one of our lectures. This is an endothermic process to turn a liquid into a vapor. So this is just another way to write that equation up here. Now, part A says, suppose the temperature is increased and equilibrium is established at a higher temperature. So we're adding heat, we're adding energy. How does the final value of each of the following compare with its initial value? In each case, stay higher, lower, or the same. So, if I add heat, what will happen to the rate of vaporization? So I'm adding heat. Won't that push the equilibrium to the right so that heat is consumed? If it pushes it to the right, I will make more gas. Now that's actually an answer to a question coming up, but it's asking what happens to the rate. If you're adding heat or energy, don't the molecules move faster? They have more kinetic energy. So the rate of evaporation will increase. Letter B, you're on your own. So read through letter B, and you need to handle that by yourself. Letter C. What is the final concentration of vapor molecules? Now, when equilibrium is reestablished, I sort of just answered that for you a few minutes ago. When I add heat, won't it shift the equilibrium to the right to use up that heat? So won't I have more gas at the new equilibrium than what I had at the older equilibrium when it was colder? So I claim the concentration of gas particles will increase because the equilibrium will have shifted to the right. Letter D, that's another one where you are on your own. Okay, I'm not going to do all of these for you like I stated earlier. Okay, next up is number 34. Number 34 says, given a sample of water at any point on the curve AB in figure 16. Now, when it says figure 16, it's referring to a figure in the chapter. Figure 16 is on page 347 of your textbook, and it happens to be the phase diagram for water. So, if I turn to page 347, and if I look at the very bottom of the page, it says phase diagram for water, and you are interested in line segment AB. Now, if I could draw a crude representation of that phase diagram, it looks something like this. Line segment AB is from here to here. Now, this is solid, this is liquid, and this is gas or vapor. So it wants to know what happens along this, it wants to know what happens when you change pressure. Remember, this is pressure, and temperature. So let's take a look at just a couple of these. Letter A, adding energy at constant pressure. So for letter A, we are going to increase energy. Isn't that the same as increasing the temperature? So if I'm along this line and I add temperature, won't I go from solid to vapor or solid to gas? Remember, temperature is increasing. So I will go from solid to gas. Okay? So what effect would each of the following changes have on the sample? I would make gas, right? It would, let's see, we're going from a solid to a vapor directly. What do we call that? Sublime or sublimate. Letter B. I'm just going to give you a hint here. When it talks about decreasing volume, that's what letter B says, decreasing volume. That's the same as increasing pressure. So think of it that way. And that's the help I'm going to give to you on letter B. Letter C says we remove energy. So lowering energy would be the same as what? Lowering the temperature. So think of it that way. And then letter D for number 34 says increasing the volume. Now, if decreasing the volume is the same as increasing the pressure, what do you think increasing the volume will be? Increasing the volume will be the same as lowering the pressure. Okay, so that's your help. So take a look. You have pressure on your y-axis, temperature on your x-axis. Try to figure out what happens, whether it will be forming a solid or a gas to a solid on number 34. And then finally, your last question on the assignment, number 35, I am not going to give you any help. Now, if you want help, you can come in before or after school and I'll help you. But on this video, I'm not going to give it to you. Alrighty? Well, that's it for assignment 31. Good luck, and I hope this helped you. Bye-bye.